Well, hello friends, and Merry Christmas! Today we are going to do something a bit unusual on this channel. We are going to work on somebody else's programming project. And I saw this tweet by Tim Morgan a while back about looking for contributors for his Natalie project. And this was back in July when he had 9 contributors, and then he's been posting updates to this Twitter thread whenever somebody becomes a contributor. And they're now at 18 as of 13 hours ago. So I thought we could, join in the fun and contribute to the project. And if you're not familiar with Natalie, it's a Ruby to C++ transpiler, I think you would say. And I don't know Ruby, so this is going to be a little bit confusing, and I've never worked on Natalie, but I have watched a bunch of Tim's YouTube videos, so I'm going to link to Tim's channel in the video description because Tim makes compiler hacking videos, much like I make operating system hacking videos. So he has lots of videos about working on the Natalie language. If you want to check that out, definitely recommend it. And I've seen a bunch of his videos, but I never actually tried to work on Natalie, so this is going to be interesting. Yeah, so that's what we're doing today in the spirit of Christmas. And I'm just gonna take this off because it is a bit warm. Anyways, let's see. Let's get started. So let's check out the code. We'll just grab it off of GitHub. And then how do you build that? You don't make, you have a gem file and a rake file. Does that mean that you can rake? Maybe I should read the instructions. Okay, building. You need these, okay. And then you need to do these commands. Okay, so we need to do a couple of things. Let's do one at a time. So, okay, so there was a submodule, and then we need to install bundler. It sounds vaguely familiar. I wonder if I've installed this before at some point. Anyway, okay, so rake. Okay. So let's see how this thing works. Usage. You get a REPL with bin Natalie. Let's start with that. 1 + 2. 3. I think that's correct. So this is pretty cool because what happens when you type something into the REPL is that it generates a C++ program and then compiles that program and then runs it. So that's why it takes a moment after you hit enter before it actually prints the result. Whereas I guess the native Ruby, does that work? Okay, maybe it doesn't work that way. I don't know. I've never used Ruby as a REPL. And okay, so now what can we do with this? We can run a script. Okay, right. So you can pass in a Ruby program, and then it just compiles that program into C++, compiles to C++, and then runs that executable. And you can also compile a file into an executable. Yeah, right. Okay, so this then gives you a hello executable, which you can run, and then it's super fast. So that's pretty cool, actually. So what do we want to do today? Well, since I don't know this project, one way I find really enjoyable to learn about new projects is to do some performance analysis. So let's look at the performance of something. And I guess we're going to have to make a little performance test. So how do you make a loop in Ruby? Loops. Okay. A while loop is just fine. While conditional do some code and then end. All right. So we'll call it loop.rb. While conditional. I'm gonna need an example. Oh, this is perfect. Okay. So while x is less than 1 million, end. Okay, and then do we have to declare x? Okay, and then x, can we say x plus plus? Is that a thing? And then maybe we'll like put x at the end. No. Unexpected end. Or maybe x plus plus is not a thing. Can we do this? That was a thing. Okay, and let's see if Natalie can run this program as well. Yes, it can. Okay. So let's see how long that takes. So let's compile that to a standalone executable loop. Okay. How long does that take? Almost a whole second. Holy moly. That is a long time. Okay. And if we just run it with the native Ruby, that runs in less than 100 milliseconds. So we have a serious performance discrepancy here. Let's investigate. I guess we'll start by getting a profile. Just run it in call grind, and then use kcache grind to take a look at the result. Guess it's going to be a large profile. Yeah, I have written less than 100 lines of Ruby in my life, so bear with me as I'm really not familiar with control flow or anything. Okay, this is obnoxiously slow. Maybe we should have made we should make a shorter version of that test. Oh, okay, now it finished, finally. All right, so what are we doing? Can we get a call graph? Okay. Right, so we are looking at time spent. So here's main. As you can see, almost all the runtime is below main. And we're entering into eval, which then calls public send. And that's like virtually all of runtime is within public send, sure. And then calls some other public send, and then we start to see some different things happen. The graph is really simple though. If you look at the whole graph over here, it's a very simple program that we wrote. But why is it taking a whole second to run? That's what we need to find out. So, what is this doing? Public send. So I guess it's like sending a message to an object or something like that, sort of like an Objective-C. I'm not sure. I'm not super familiar with the architecture here, so let's see. We have find method, so looking up a method, and we have calling a method. Presumably public send first looks up a method, and then if it finds one, it calls it. Okay, so then we are calling two main methods. We're calling integer value add public binding and integer value LT public binding. Okay, and then they just forward to member functions in the integer value class. And both of them call value putter operator arrow. And then that turns around and does a hydrate. And aha. Okay, so now it gets interesting, right? So here we can see that hydrate calls operator, it calls a heap allocator, right? So we're doing a heap allocation from the Natalie garbage collector, and that's probably a large part of why we're losing so much time. And then what's even going on here? This is, wait, so hydrate has two cases. Either it allocates a new GC object, or no, it doesn't have two cases. It allocates a new GC object and then it invokes the integer value constructor. So presumably integer value is a GC allocated object. And then it seems like we are losing a bunch of time in the hash map stuff. Std pow. This looks really unfortunate. Like just doing pow, spending like what, like almost 10% of runtime in pow. That's crazy. Although this makes me wonder, is this a debug build that I got here? Or are my programs debugged? Like the generated programs. It's like 9 megabytes for that program. That sounds like it might be a debug build. What did they say here? Debug. Currently, the default build is the debug build since Natalie is in active development, but you can build in release mode with rake build release. Yeah, that's what we should do. So how do you, can you just rake dist clean or whatever? No? See list of available tasks with rake tasks. Rake clean. Okay, and then rake build release. Okay. Bum, 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 bum. Then I guess I have to regenerate these things. So let's delete the ones we had and generate a new one. So Natalie loop RB. Okay. All right, that's a lot faster. So now it's like about 300 milliseconds instead of about 1 second. That's a lot better, but it's still significantly worse than the native version still, which runs in less than 100 milliseconds. So, but we're no longer 10x, 10x worse. We are 3x worse, let's say. So let's get a new profile. Hopefully it will be a bit faster. Okay. And then let's open that up. Okay, so looks the same over here. Eval. Still doing a lot of all the same stuff, of course, but just runs faster, and we no longer even see that that whole thing with POW that's like eliminated. And now we're we're still spending like a third of runtime in hydrate. So I guess what we need to figure out here is why do we think that we need to do GC allocation when we're just like incrementing an integer and comparing it to 1 million? So let's investigate that. Okay, let's just open this up in CLion. I don't know if CLion's going to understand this type of project, actually. I will see. So let's go. What do we want to look for? I guess we want to see... why does less than call hydrate? And let's also verify what hydrate is. So hydrate, value putter hydrate. So if the type is type integer, then we temporarily disable the garbage collector, create a new integer value object, then re-enable the garbage collector, and zero out m integer. Wait, m type. What? Okay, so value putter. What is value putter? Value putter is something that is either an integer or a pointer. Okay. So I think this is sort of an optimization thing where you're supposed to be able to pass around integers without allocating a GC object, but maybe that's not like fully fleshed out, because it seems like for even basic operations like adding and doing a compare, we still end up reifying the value putter to a GC object. Let's figure out why. So let's look at integer value LT. Okay. So can we see the source code here? Okay, integer value LT. Where is the... Wait, who turns it into a hydrate thing? The call to hydrate is in operator arrow. It's doing operator arrow on something, and that calls hydrate. So who does that? Hydrate. Oh, is it value putter? Okay, so you have a value putter that presumably you start out, like if you instantiate an integer, you start out by creating a value putter that has no GC object. Actually, can we see the generated code? Keep CPP, yes. Loop RB. Okay. Okay. And so this is the C++ code that Natalie generates, and this is what we end up running. It's a little bit hard to read, which is to be expected for generated code, of course. So what's going on here? This is, we enter here, I guess, in this try block, and then value putter x2. Okay, so here's a constant, the 1 million constant, that one I remember. So you create an integer value putter via value putter integer. Let's see how that works. Integer. Okay, so that's like a factory function that gives you a value putter initialized with a whatever a nat int t is. Long, okay. Okay, so the operator arrow on value putter causes a hydrate, and we are an integer, which means that we switch types to pointer. Right, so if you dereference a value putter with the arrow operator, then if it was an integer before, it now becomes a pointer. Okay, a pointer to a GC allocated object. So basically, in order to avoid GC allocation, we have to make sure that we don't dereference value putter if we can avoid it. So already here you can see that we start by dereferencing it. So at this point, like, it already will turn this value putter into a pointer, which is unfortunate. So like, yeah, it always becomes a pointer at this point. Okay, so and really what they want to check here is like, is it a floating point number, I guess? So how does that work? Is float. So if type is integer, it cannot be a float. Yeah, right. Wait, hold on. Value putter is float. Value putter is float. But, wait. Did I see that right? Here we're dereferencing. Oh, this is so subtle. I think we're dereferencing the value putter, which gives us a value. But what you really wanted to do is just other dot is float, because you want to call it on the value putter. Because if you call it on a value putter, it will short circuit if the type is integer. So that will avoid, then we'll avoid at least one case where it would become a GC object. Okay, so if it is float, so let's imagine that, okay, so it's not a float. And then we're checking if the other is an integer, which I assume, yeah, so this will succeed because it's an integer. And that means that we don't try to coerce it, sure, okay. And then if other is integer, then other as integer is big num. Okay, so I guess here is support for numbers that are larger than 64-bit integers. But there's another arrow operator right here. So this will again force promotion to a GC object. So I think what we want here is like, we want to be able to do that essentially, so that we don't dereference the value putter. Does that make sense? So we have to implement value putter, whereas like is integer. We need is big num, bool is big num cost. Or actually it seems like maybe this project is not, maybe it's not const aware. So let's just be consistent with what's already here. So is big num, how does that work then? So I guess it's similar to is integer or is float is big num. So if the type is type integer, it cannot be a big num. So that's our short circuit path out of here. And then value has to be an integer. So wait, what does value do? I think value will hydrate. Yes, value hydrates. Okay, so that's our hydrating thing. And then is big num, like that. Okay. And if the other is big num, at that point, yeah, at that point it's okay to use the deref operator or the arrow operator. So, oh, and then at the very end here, I guess this is an exceptional case. So we're raising an exception. So in that case, that's going to be unusual. So I don't care about the arrow operator in that particular case. So I think we now got rid of all the arrow operators in the basic integer path. Let's verify that we actually got that right. What was it? Release, build. Oh, you can tab complete these. Oh, that's so cool. Okay. What was the other one? Wait, let's go back to the top. The other one was, this was LT, the other one was add. Right. Okay. Still about the same. Okay, let's see. Wait. I have to actually build a new. So let's call that loop original. And I have to actually build a new one. It's a little bit of an unusual workflow. So, okay. So that looks healthy. So we've already chopped a little bit off here. So we're down from 0.29-ish to 0.22, say. Looks healthy. Let's see that it actually looks right in the profile as well. So we'll do that by just checking that integer value LT no longer ends up triggering a hydrate on the value putter. Okay, so bringing this up right here. Okay, so we have LT and add, and yeah, look at that, super nice. So we now see that LT doesn't actually call anybody else, whereas the add stuff ends up calling things. So I think unless you have like integer overflows or like you overflow the capacity of a basic 64-bit integer, so you have to switch to a big num storage, we should be able to avoid hydration in the add case as well. So let's look at that. Integer value add, right. So where is the, can we see where the, let's look at the source code. Hydrate is once again from operator arrow. Add public binding. Oh, wait, you want to look at this guy. Arg. Where's arg arrow? Ah, right here. Other is arg arrow as integer. So here we screw everything up and get off the fast path and doom ourselves to the slow path. So we need to avoid doing this. And as we can see here, we already, like if arg is not an integer, so if it's a float, we do blah, 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 and then return. If it's not an integer, then we will coerce the arg into an integer and then somehow assert that the type is now an integer. So let's see. Can we rewrite this so that we avoid the arrow operator? If arg is big num, which we now have, we can do something like this, like arg as integer to big num. Or even for simplicity, we can just move that into here actually. Okay, that seems fine. And was that used elsewhere? Here. Okay. Wait, what does this do? So if it's a float, blah, 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 return, coerce to int. If arg is big num, then handle big num, sure. And then, okay, so here we add together the two 64-bit integers and we check for overflow. So if we overflow, we have to use big nums instead. That's fine. Okay, so I think we can do this down here as well. In the overflow case, we'll just do that. Okay, wonder, was that enough to... Okay, we messed something up. Other was not declared in the scope. Okay, that's my bad. Oh, did I not put it back? Wait, where am I? Oh, I'm in the wrong function. I was in sub suddenly. Yeah. Sorry, I was looking in the wrong place. Okay, great. LT fixed. And then let's create a new thing here. Ooh, look at that runtime. We're almost cut in half from where we started. Super nice. Okay. Let's get a profile of that. Okay. So what do we see now? Both of these branches here lead nowhere. They just stop here. No GC allocation through hydrate. That is just spiffy. Does anybody call hydrate? There's still people calling hydrate. 4 million calls to hydrate. Oh, there are calls to hydrate. Wait, from where? Wait, who was calling that? Oh, it's the bindings layer, I guess that's calling it. Okay, so how does that work? What was it called? LT public binding? this looks very generated. So what was it called? Integer value, add public, LT public. Okay, so these kind of functions are the ones that then forward to the C++ add function, for example. Sure. And we have a self value coming in here, which we unconditionally convert to an integer, and there's the arrow operator that hydrates the value putter, turning it into a GC object. So effectively, when you use the add operator, or you do less than on an integer value, it will be promoted to a GC allocated integer value object, whether you like it or not. And I don't know exactly how to approach that because I'm not familiar enough with the architecture here, but it seems to me that the code could be arranged in such a way that this promotion doesn't have to occur. So perhaps you could factor out the add operation into a standalone function that optionally handles, like has a special case for value putter type integer, so that you can sort of short circuit in that case. Like if you're adding together two integer value putters, you can have a short circuit path, just validate that there's no overflow possible, and then add them together and return an integer typed value putter. But yeah, let's not get into that here, because that would require, I guess, changing how the bindings are generated and how a lot of things work, actually. So still, there's room for improvement here, but and yeah, there are still 4 million calls to hydrate, although it is interesting that these don't actually seem to GC allocate. How does that work? Hydrate. Or am I just not seeing the GC allocation? Self value as integer. So wait, hydrate is always called. Oh, wait, so it's not like hydrate. It's not conditionally called. It's always called. So it's going to be called even if the type is pointer, in which case it does nothing. So we could probably improve the profile somewhat. This is actually like more speculative, but like if type is, or let's call it something like hydrate if needed, right? And then and what this guy would do is just like, if type is type pointer, then just return, otherwise hydrate. And then you don't end up actually doing the function call if you can determine right away. Assuming that this gets inlined, then you can dodge making the call to hydrate. It's probably not a huge deal, that call, but Oh, let's investigate. So loop rake. Yeah, it really feels like this value putter integer storage optimization. Like we're barely scratching the surface of all the potential mileage you could get out of an optimization like this, and you could expand and also cover like other types like floating point numbers, and I don't actually know what kind of primitive types Ruby has. But I imagine that there are more types than just numbers, or like, I guess you have Booleans, for example, which you could also avoid having to GC allocate. Let's see. Yeah, it's kind of the same. Okay, so let's make a patch out of this, I guess. Gap. So we'll skip the hydrate if needed stuff, since it wasn't like a huge measurable improvement. And we need is big num is one thing that we're adding. Oh shoot, did I actually nuke the I did. Okay, is big num. Okay, so let's do that as a separate commit. So let's look at their commit message style. Looks like descriptive commits. Actually, do they say something in their contributing document? See, use Clang format, sure. Split changes into atomic commits. Yeah. Wrap your commit messages, even the subject, sure thing. Okay, this is extremely familiar. So it's basically same type of commit messages as Serenity, just missing the category thing that we do. But here, I mean, it makes sense that you don't need to do that here because it's like, obviously the scope here is a lot smaller than the Serenity project. So everything is sort of in the same category. Add value putter is big num. This function allows you to query to determine a value putter contains this function tells you whether value putter contains a big num without promoting I don't know what to call these, like type integer value putters. Let's call them type integer value putters. To GC objects, or GC, yeah, to GC object. Yes. Without incidentally. Yeah, incidentally. That's like as a side effect of, right? Incidentally, let's look that up. In an incidental manner, as a chance occurrence. By accident, in passing. Yeah, that sounds kind of like. But you know what? That's not the clearest language. Let's see. without the side effect of promoting full GC objects. Yes, there we go. And then there are probably more cases of these actually in integer value. So let's look at like greater than. Yeah, so you have the same type of problems here with greater than, less than, equals, and so on. So we could, yeah, it's actually kind of internally inconsistent because look at greater than equals uses other dot, no promotion. Then you have greater than uses other arrow, so that does promotion. So you want to do like that. And like that, then you should be good. Yeah, so I think we can actually fix a bunch of these. Other arrow, subtraction, same basic issue as addition. We just move those in there, no trouble. Okay, multiplication, again, same issues. No big deal. Division. It's interesting how this is implemented. Like arithmetic operations are like functions, member functions on the integer value class. I guess that means you could, can you like add together strings and stuff? Like string value add, is that a thing? Yes, it is. What about string value mul? It is a thing. Okay, that's pretty cool. Yeah, so I just don't know how Ruby works, so that just looks cool to me. Bam, 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 bam. Do we have a bunch of other? That looks avoidable as well, and that. Okay. Yeah, I think that's it. So this feels kind of sloppy, but I think it's a good start. Or at least if I got everything right. If other is big num. Oh, that's arg is big num. Sorry. Yeah, I guess I got a bunch of those. Okay. And let's see that it still works. How do you run tests here? Rake test. Is that a 38-minute ETA on the test suite? That's a little bit much. I don't think I'm gonna show me waiting for that. But I think this turned out pretty good. So let's just work on our commit. Yep. Strive to try harder to avoid hydrating value pairs in integer value functions. Use for value type integer value putters. We want to avoid promoting or hydrating them into full GC objects whenever possible, since GC allocation is slow. This patch updates various integer value member functions to dance around the the implicitly hydrating value putter operator error. In the common cases. Yeah. So that made our like silly little loop program run in about half the time. So it's like literally doubling the speed of that program altogether. That's pretty cool. Although now I want to reword that commit right here because I said promoting, but let's say hydrating instead of promoting. Yeah. Without the side effect of hydrating, and then we'll say into full GC objects. Yes. That's nice. Okay, well, no trouble here yet. I think this is probably going to be okay. So let's make a branch. What do we call it? We'll call it, or actually, I should also explain what this makes faster, the last commit. This simple example program runs roughly twice as fast as a result. What was it? I0 while I 1 million, I plus 1, and yeah, there we go. Let me just verify that that was the actual program. Yeah, it had the puts X at the end, but I think we can live without that. So get branch, less hydration, less integer hydration, less integer hydration. That's what we'll call the branch. All right. And okay, and then let's push our branch to GitHub. Oh shoot, I didn't check this out. Okay, let me see if I can. Okay. Here we go. So let's change that. Git config. We'll just change this to that. Oh, shoot, I need to fork it. We'll fork it right here. That's the origin. And then we need to add a remote. call it mine. There we go. Compare and pull request. Okay. Here are some patches to keep us on the happy path more often. And avoid hydrating. By avoiding hydrating, type integer value putters. These changes, a simple loop, increment loop, runs twice as fast. Let's see. Don't want this looking untidy. Wait, why did I indent that so much? Okay. Hello, friends. Let's say. Yeah, I think that turned out pretty good. We'll see what they think about that. All right. So, still running the tests, of course, but we're just gonna assume that that works out. Otherwise, I'll have to update the pull request, of course. But yeah, I think we will just finish the video here, and unless something goes horribly wrong, I'll just put a link to the PR in the video description so you can see how it went. But yeah, this will be the end of the video. So thank you very much for watching. This was certainly unusual. It's been a while since I picked up somebody else's code and hacked on it, but I think we identified an issue pretty quickly and were able to improve the situation, doubling the performance of this thing. Of course, we're still pretty far from native Ruby performance, but we have significantly narrowed the gap, at least. So it's good progress. If you are interested in contributing to the Natalie programming language, definitely recommend checking out natalielang.org. And I think there's all kinds of stuff to do because the Ruby implementation is young and there's lots of missing functionality. So yeah, actually they have a graph right here showing spec compliance over time, I guess. But I went straight to performance work instead, because that seemed like the most interesting thing to do today. So anyways, I hope that you enjoyed the video. Definitely outside of my comfort zone, but I think it went okay. So thanks for hanging out, and I will see you all next time. Bye. Merry Christmas.